Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. It's my pleasure to reintroduce Pascal Foy, who gave us a talk yesterday on feature descriptors. Pascal is a professor at École Polytechnique Fédérale de Lausanne. He's done a lot of work in stereo matching and feature detection and also person tracking, and he's going to tell us about the latest work in that area.
Thank you. Okay, so what we've been doing in the area of people tracking is to work on a multi-camera system that ought to be able to follow a number of people in potentially crowded space where people occlude each other. Which means we have images like those, and from those video sequences, we'd like to produce 2D trajectories. And ideally, of course, we'd like to be able to do this over long periods of time, using cameras that may be above, that's actually easier, or, as is often the case, at head level. And this is important because it causes occlusions. So actually a lot of what I'm going to talk about is how do you deal with occlusions and how do you put together a system that is robust to that. And of course, we'd like it to work in realistic scenarios where you have thousands of frames, long sequences. The typical type frame would be, I'll mention basketball later, so a whole period of basketball it should track. The images may or may not be of good quality. So for example, we'll see these are images from a subway, an underpass, where the lighting is bad, the resolution is not wonderful. Has to be able to handle that. And of course, as soon as you go outdoors, you have to deal with shadows and illumination changes and all this fun stuff. That makes life more difficult. So the algorithm we put together works in two different steps. It does its reasoning in the ground plane. So we imagine that we have an area we want to model in which people are going to walk in and walk out. We discretize that area. And in the first step, we are going to compute the probability of occupancy at each time frame independently. So no temporal consistency at this point. We just, at every instance separately, we estimate how many people there may be in the scene based on what all the cameras see. And then, given these probability occupancy maps, we'll then enforce temporal consistency under very, very generic assumptions. Essentially, the only assumption we're going to make is that people do not teleport.
You also assume two cameras?
Two or more.
Two.
Actually, I'll show you that to some extent it actually works with one. The formalism can handle one, but it's really designed for 2, 3, 4. So here's the kind of input we are going to work with. So we have two graduate students, two naive subjects, as they're often called in these cases. And what we do is we run a very simple vanilla background subtraction algorithm that does something like this. And the reason I'm showing this is is because you can see this background subtraction is not particularly good. And that's actually realistic, and that's what's really going to happen in real situations. So you are going to need an algorithm that can handle this. And by the way, since we are at Microsoft, I'm using background subtraction because that's something we've been using for a long time. But if you feel like using the output of the Kinect, you could. Actually, if you are in a situation where the Kinect will work, the output will be better than this. It will actually have more information than this. And so everything else after that should work even better. But for the time being, we are going to work with this. And so the game we want to play in this first stage of the algorithm is, given multiple binary maps like those, compute this probability occupancy map, which is just something that says that every grid cell, there is a certain probability of a person being present. So of course this one indicates that there are probably two people, one here, and there's a bit of noise. And this actually is not binarized. It's a set of floating point numbers. So how are we going to get those? So let's try to formalize this a little bit. So what we're going to try to compute is the probability of there being people, so x1 to xn are binary variables that say whether there is or isn't a person at location I, grid cell I, given B1 to B capital C, which are the binary maps. And so this is going to be done at individual multi-view timeframes, so at one given instance. We should expect the B's to be very noisy. And we should take advantage of the fact that the size of the B's gives us some very rough estimate of how far the people are. And most importantly, it should be done in such a way that it robustly handles occlusions. So to estimate this, which is of course a complicated probability distribution, the first thing we are going to do is a mean field assumption, which is where we are going to write it as a product of local probabilities. This is, I'm not actually making any independent assumption here. I'm just defining the variables of my optimization. So I'm going to write Q as a product of the small q's, and the small q can be interpreted as the probability of presence in any grid cell. And to compute them, what I'm going to want to do is to say, well, I'm going to choose my q's so that these two distributions are as close as possible. And one way to say this is I want the KL divergence to be as small as possible, so I'm looking for an extremum, a place where the derivatives with respect to the small q's are 0. So, of course, it's easy to write, but you actually have to compute this. So how are we going to compute this term, which is essentially, this is the data term, the probability of presence given the binary blobs. So the first thing you do is the standard Bayesian reformulation.
So the capital X is like a set of X cases.
I'm sorry?
You have this XK. So you have no over the top. This QX is like PXK. So so X contains many cases like that. Capital X.
Yeah, so X, capital X, is a vector of all the locations. So it has, basically it's a binary vector whose size is the size of the grid.
Oh, so it's the entire floor.
If I go back to this, sorry. What I'm calling capital X without an index is the variable, it's all these guys.
Right.
Which are all...
X is like everything.
It's everything.
Okay.
So, that's standard Bayes reformulation. I need to actually estimate the probability of B knowing X and the prior probability of X. So let's now make a couple of independent assumptions, which are first, I'm not going to take into account the interaction between people. So I'm not going to take into account that if I'm in this grid cell, the probability of somebody being in the grid cell next to me might be affected by that. So I'm going to write this P x1 to xn as just a simple product of the prior probabilities of being somebody in a grid cell, and that's going to be a constant. And then the second one says that all statistical dependencies between views are due to people being present and moving. In other words, in the scenes I'm dealing with, the only thing that is moving are the people. The furniture is fixed, there's nothing else, and that means that the probability of if you know where the people are, then the probability of observing a particular binary image in any different image are conditionally independent, which I write this way. So when it comes down to it, the only term I really have to estimate is this probability of observing a pure binary mask if I know where the people are. And to do this is actually fairly simple. I'm going to use a very simple generative model. If I know there is one person, there's a person here running around the room, here are the images I expect, the binary images I expect to see. So in other words, what I'm representing a person as a cylinder. And if I know I have a person at a given location, the image I expect to see is a rectangle at the appropriate location that is given by the fact that my cameras are calibrated. Here is, for example, here is what I would expect to see if I knew there were exactly 3 people at 3 specific locations. And what I'm going to do essentially is compare this image to the image I actually observe. And one strength of this, which actually is not shown here, is that it will handle occlusions naturally. So if, for example, this person was behind this one in this particular view, the fact that I'm using a generative model will handle this automatically, and the synthetic image I would produce would naturally take into account the occlusion without any complicated reasoning, which fundamentally is the reason why we formulated this in this particular way.
You literally actually you just synthesize this image.
I'm sorry?
You synthesize this image.
Yeah.
And then you compare with
the one. I'm going to do that. What I'm really going to do is I'm going to adjust to put ones at the right places so that this image looks as much as possible as the image I observe. And I mean, we could have gone a different way. We did at the beginning. We could, instead of having a generative model, you could say, I have blobs in one image. These blobs define a cone in which a person might be. And then you do that for all possible images and you intersect the cones. So we tried that, but what happens if you do it this way is then you have to do some real reasoning about occlusions and people intercepting the cones, and it becomes a massive headache very quickly. And this is why we switched to that particular way of doing things. And I have to introduce one more concept, which is I've talked about this synthetic image that was based on the idea that I knew exactly that with probability 1, the Q's here are probability numbers. So if I know with probability 1 that there are 3 people at 3 specific locations, I expect to see that. But now, if I know not with probability 1, but I know with some probability between 0 and 1 that there may be a person at these locations, what kind of image am I expecting to see? And so what I expect to see is something like that, which I'm calling the average synthetic image, which is if you drew many, many distributions of there is or isn't a person using those probabilities, generated synthetic images, and average them, you would get this, which is this average synthetic image, which I'm going to use. So this is the one you get if you assume that at these 4 different locations, you have a person with probably 0.2 for each one of the 4.
Very computationally expensive when you compute the average synthetic image.
No, because you don't. Okay, so here there's a bit. That's where the mean field assumption comes in. What you do, the computation is actually trivial. What you just do is you paint something with the rectangle, instead of putting 1, you put 0.2. That's it. I don't explicitly do a Monte Carlo simulation every time.
Oh, I thought you randomly.
No.
Oh.
I don't, because yes, indeed, that would be horribly expensive. This is a slight approximation. It's known as the mean field approximation. And so maybe I should call it the approximate average synthetic image.
But why is 0.2 so propagated?
It's not, it's just as an example. I mean, it can be any value, because in fact, what we're going to compute those numbers in the end. So, back to what I'm trying to estimate. I have this is the result of my binary subtraction. So these are the blobs that my background subtractor gave me. And let's say I put people here with some values and I create a synthetic image. What I want to do is measure the distance between these two images. And what the measure of distance is going to be very simple. I'm going to define this function psi, which actually depends on their respective overlap. And I'm going to estimate the probability of observing these blue blobs given x as just e to the minus this distance, e to the minus psi. So if the black rectangles and the blue blobs are perfectly superposed, this will be close to 1. If they are completely disjoint, it will be close to 0.
So the distance, the subtraction is literally just it's like a pixelwise.
It's pixel-wise. Yes. And that's important, of course, because it's going to be fast. And also, I'll get to this, is not only is it pixel-wise, but because the avatars are rectangles, we will use integral images to compute them, and that's how we're going to get the real-time performance. And so this term I was trying to estimate the probability of B observing all these binary images given the probability of presence is going to be this estimate at this product of the E minus psi, of course, with the usual normalization constant that I will ignore when I look for a maximum likelihood.
You're assuming a certain particular height, right?
Yes, I'm assuming, so it's 1.8 meters.
So if a child moves around, then you're in trouble.
No, and I'm going to show you why in a second.
1.8 is kind of tall.
No, sorry. Okay, so the answer, a child that's taller than 0.9 centimeter, 90 centimeter, who's taller than half the standard size will be fine. Actually I have this video. So back to what I was trying to do, which is I'm trying to make these two distributions be as close as possible as a function of those Qs. I'm minimizing the KL divergence, and I've expressed this P of x knowing B as this product of distances, of exponential of minus a distance between the binary images I've observed and those average synthetic images. And what's important to note about this, it doesn't show, but this is also a function of the Qs. Because the average images are a function of where the people are, so all of this is a function of Q, so differentiating with respect to Q makes sense. And in the end, if you work out the math, what's happening here? What ends up happening is you get the minimum when Q at location I can be expressed for all Qs, for all locations. You have this, it has to hold, so this looks like a very ugly expression, but in fact it's fairly simple. What this is you take all your probabilities of presence and you take the one you're trying to estimate, which is at location I, and you compute two different average images. The one where the corresponding Q is forced to 1, so definitely there is somebody. And the one where the same Q is forced to 0, definitely there is nobody. So you get these two synthetic images with and without somebody at location I. And you compare the distances given with all the other Qs being fixed. So basically what you are measuring is if I put a person in this location, do I improve the distance? Or do I improve the distance by removing somebody? And when, so this is what this term is. And when it is balanced, you are at this form of equilibrium and your KL divergence is minimized. And okay, the formula doesn't matter that much, but the point is all of this can be computed very, very quickly. You just have to compute this psi by doing a few integral image computation. It's very fast. And what you end up is a simple iterative scheme where you start the algorithm by having these q's being some small values, the same small value everywhere. And then you iterate this operation until it stabilizes, until you find a fixed point of this iterative scheme, which typically takes 4 or 5 iterations. Doesn't take very long. So to make this a little bit more visual, first an interpretation. Okay, so you have these binary masks, and you are computing the Q's so that the average synthetic images are as close as possible to these masks in all possible views simultaneously.
So,
yes.
Yeah, I was just saying, in this particular case, you have floaters, right? That's
Right.
sort of cut off. If the person, which is separated to, is much closer, then that part might be misinterpreted as being far away.
Yes, but that's why you need multiple cameras. So what's going to happen is, and we'll see it in the next slide, if you have only one camera, you can do what I just described, and what you're going to get is this probability of presence being kind of elliptical, spread along a line of sight. But because you have multiple cameras, what you get essentially is the intersection of these elongated ellipses, and then the ambiguity goes away.
So that was my question. So the cameras actually are their optical axes are almost orthogonal to each other. They're not two cameras.
No, it's meant for wide baseline, and basically it would be meant. I would put the 4 cameras here in this room are perfect.
And they're synchronized.
And synchronous, yes.
And so you're not using the information that the lower contact point of that thing roughly tells you where you are.
No, because as you've seen, oftentimes the legs can be cut off, and the background subtraction is just not reliable enough for this.
So these boxes, the generative model is also very coarse. Right? So it's not like you actually have a articulated model of
No.
human.
But it seems to be enough. I mean, okay, so I imagine if you were to have acrobats who are in all sorts of funny positions, I'm not entirely sure what would happen. But you'll see in a moment when you look at, say, at basketball players, which do move quite a bit, it's good enough for that. Okay, so what you're seeing here on this slide is, with 2 cameras, is this iterative scheme happening. You start with kind of a small uniform probability distribution, and pretty soon it converges to this very peaked thing, where this is the result, where what you have is a very high probability of there being a person here, and a bit of residual here, some small numbers because of noise, and because indeed what's happening here is the person here, for some reason the blob, actually that's what we just discussed, is a part of the blob here is outside of the rectangle, so it's not completely explained by this rectangle. So it compensates by that by adding a little bit of probability shown in blue here. That corresponds to this. But in fact, the result is still very peaked. I mean, this is light blue indicating it's a value that's not 0, but that is small. And the black here indicates a value that's very close to 1.
Why is that black spot not blurred?
The
shouldn't it have been a blurred peak? Like
it should have, but because what's happening is this, the result is so peaked that the blur is almost imperceptible. And here is another result with two people. So say again, it's the same idea, where it converges very quickly to a distribution that's very peaked with two peaks corresponding to the two people. And actually this blob is interesting. It kind of answers the question about why don't we use the feet? Well, in many cases, the feet are just not there.
Do you need to know how many people?
No. No, because essentially it will introduce, it has blobs, and it's trying to explain those blobs. So it will introduce blobs, squares, as many black squares as it needs to explain what it sees. So now it's the same thing, but over time. So now the previous video didn't have time in it. It was just what you did at one iteration, at one time step. And now what I'm showing is this probability distribution as the video goes, the converged results, but still without temporal consistency. So all these maps have been computed at each time step independently. So this is, I've shown this. You can see that occasionally you see a bit of blue in this thing, which is when it's not so sure anymore. And typically that happens when a person is visible in one camera but not the other. Okay, it's three people. Same idea. So you can see that one of the dots is a little bit blurred once in a while, but not that often. And now to your question about people sizes. Here is what happens when what's happening is the person is growing as you during the video. So the size of the person is changing. And what you can see is the algorithm is not terribly sensitive to that, especially when a person is seen in more than one view. So the black, what you're looking at is a person he's not moving. Right now now he's moving. His size is changing. So at some point he's bigger than than 1.8 meters, and at some others he's smaller than 1.8 meters.
How do you do experiment?
Oh, but since that's completely synthetic, so we give. This is basically, we decide that this is the output of the background subtraction, and we feed that to the algorithm. And maybe to make it a bit more real, here's what's going to happen. So here's a kid. So that kid is definitely less than 1.8 meters, and he is detected just fine. And let this run, because in a moment his mother is going to walk in. Okay, so here's mom, and here's little sister. And little sister is not detected. And it's not because the algorithm is sexist, it's because she's below 90 centimeters. She's shorter than 90 centimeters. And so if you look at the formulas, what's happening when you compute the difference between the blobs and these average synthetic images, basically it will put a rectangle if at least half of it is full. What it tries to do is to explain everything that needs to be explained and not explain what doesn't need to be. So you pay a penalty for introducing an avatar at a place where there is nobody. And so that's why you have this cutoff. Somebody who's half the size, it can go either way. If you are bigger than half the size, then it's the gain that you have by introducing the avatar overcompensates for the loss that you have in explaining all the top part that doesn't need to be explained. And in the case of a little girl who's too short, then explaining all that empty space above her head is too expensive, and the algorithm doesn't.
So you do the per frame independently. How do you maintain that each person has the same number that you never?
Well, that's okay. So very good.
Secret sauce.
Right? No, not secret sauces, because I'm coming to that. Is this actually is? So give me one slide. I answer to this. The key, so this runs in real time. The code is on the web if you want to play with it. And also the code is done so that for example, if you want to make the experiment of running this with a Kinect output, you could. Because it doesn't matter where the background subtraction is not part of the algorithm. It's just, it expects.
I need to fit in something, the mask.
Blob image.
Right, you need to give it blobs somehow. How you compute the blobs is your problem. And so that's your question, is what I've talked about is the algorithm that produces at every time step independently a probability of occupancy map. The next step, of course, is to connect the dots and produce trajectories. So the answer to your question is what I showed in the previous slide was the output of the two steps. I don't have the output of the first step only for the kids. So I showed the complete result. Okay, so how are you going to do this? Well, it turns out that a good way to do that is to think of it in terms of a flow problem. Why? Because you're on a grid, which is the grid on the ground, at time t. And as I said, people do not teleport. So if somebody gets in that slot at time t, it means at time t minus 1, they had to be in one of these, in one of the neighboring grid cells. And then at the following time step, they can only go to one of the neighboring time steps, grid cells, I'm sorry. And actually, for example, they cannot move. And not moving in this case means going from here at time t to the same place at time t plus 1. And so typically, actually, in practical implementation, the grid cells are about 30 centimeters by 30 centimeters, which means at 20 frames per second, people can only move by one grid cell from frame to frame. It doesn't matter, you can make it more, but of course it will become computationally more expensive if you do. So what you have, you can think of this as you have each grid, you connect them, so it becomes a graph. People can move from graph location to graph location, but in this big graph, only a very limited number of transitions are possible. Only the ones that correspond to going from one grid cell to one of the neighboring grid cells at the next time step. And in addition to this, you can think of this as a flow. So people are flowing from grid cell to grid cell, and there are some constraints on this flow, which is if at time t you have a certain number of people in that grid cell, in fact that number can only be 0 and 1, 0 or 1. But I'm introducing these notations because eventually I'm going to relax that and make these floating point numbers for the purpose of optimization. So at time t, in grid cell k, you can have a certain number of people, m. And this number is the sum of the people who flowed from the neighboring grid cells. Likewise, the people who flow out, all these people here are going to flow out into neighboring grid cells at the next time step. So I have m, which is a number of people, f, which is the flow from one cell to the next, to the neighboring one to a neighboring one at the next time step.
You can't have more than one person in a single cell, right?
No, I can't. I have, in fact, m, in the end, m will always be 0 or 1. But the reason that I'm formulating this way because I'm going to reformulate my problem as a linear programming problem. So for the time, it's purely binary. All these numbers, in fact, are 0 or 1. Because it's only there's at most one person in the cell, because they are a foot square. And of course, since there's at most one person in the cell, this number can only ever be 0 or 1. But the problem is, as we know, integer optimization is difficult. So in the end, I may want to reformulate this integer optimization as a floating point optimization with numbers between 0 and 1 to make it easier. And so I have some constraints on all these flows and numbers of objects. So the sum of people arriving is the number in the cell, which is also equal to the sum of people leaving at the next time step.
So I'm wondering why you don't formulate some sort of a decaying probability distribution function.
Decay.
Like what people do is from the previous time step, they kind of distribute, kind of add some diffuser to the neighbors.
But there is no, okay, so at this, right now there is no probability. There are really hard constraints. This has to be physical, it cannot be any other way. With probability 1. Right now there is no image data. I'm just defining, basically I'm introducing notations.
But in your input, in the initial phase, you do have the number.
It's coming.
0, 1.
It's coming, but I haven't used it yet.
Oh, okay.
Right now I'm just, okay, give me 2 slides. Occupancy, well, there cannot be more than 1 people at any grid cell, in any grid cell. And, well, the F's are positive. They are between 0 and 1. There's no negative flow. So, to make this complete, I also need people to allow people to enter and exit. So here, I have a grid at every time frame, at every time instant. And I also have 2 special nodes in my graph, which I'm going to call the source and the sink, which are connected to all the nodes that are entrances or exits. So in a room like this one, the source and the sink would be connected to the doors. In something like a basketball court, they might be connected to all the grid cells at the edge of the court. And these are special nodes in the sense that they are not subject to the flow constraint saying that at most 1 person can come in. Any number of people can enter or exit at any one time. And so, right now I've just set up a framework. I've given you a bunch of notations, defined flows, occupancies, and the like. And now what I want really to do is compute these M's. So whether they are people in those at those grid locations in such a way that they obey the constraints and are as close as possible to these numbers that my first step gave me. The first step, the one I've talked about before, the computation of the occupancy maps, gave me probability of presence at every location, but without any temporal consistency. Now I want to compute new probability of presence that are as close as possible to those, but at the same time obey these flow constraints. So are temporally consistent. And that can be formulated as essentially it's a maximum likelihood computation. It means I'm going to compute the M's, which are whether there is or is not somebody at a given location, so that this is maximized, and the Q's are those I computed at the previous step. So that means the M's are as close as possible to the Q's, but with the additional constraints I have formulated in the previous slides, the flow conservation constraints. And this turns out to, this is an integer linear programming problem. This is, in general, this is NP-hard. But in fact, because our graph is very specific, it has a very specific shape, it is, I always forget the term, it says, the constraint metric is totally unimodular, I believe is the term, which means it actually is not NP-hard. You can solve it, and it has this interesting property that if you formulate it as a linear program, which is this, which is instead of having these m's here, which are your, or treating the m's as your optimization variables, you optimize with respect to the f's, the flows. I mean, the m's are a function of the flows. The m's are the sum of the m's, so it doesn't change very much. And you can maximize, in fact, this. This is the same formula as I've written before, because the sum here is just m, under all these constraints, which are the flow constraints I introduced before. And this is a linear programming problem. So the additional trick that you play, and which is why I've introduced all these notations, is instead of treating the f's as binary, as 0 or 1, you treat them as floating point numbers. And you solve this problem for those floating point numbers. And because the problem is, the constraints are totally unimodular, what happens, and what provably happens, is when it converges, the f's are binary. So you treat them as floating point numbers, but once you've done the optimization, you get zeros and ones. And that's what we've done, and that works pretty well, but actually is fairly slow. So it turns out you can do the same thing faster using what's known as a k shortest path algorithm. And the k shortest path algorithm is an algorithm, it's a bit like the Dijkstra algorithm in this graph, except that instead of finding one path, the best path, you find the k best path with an s at the end.
Does it require all the frames to be in the buffer?
Yes. So it's not tracking. It's really, it's batch processing. So we do this on batches of about 100 frames. It's actually one of the things where we get the robustness. So it's not, so I'll show that later. It is real time, but with a delay because of the 100 frames. So here is the kind of results we're going to get. So we put several cameras at at both ends of this subway underpass. And this is actually not a very easy sequence because it's not very crowded. But the lighting is terrible. And the cameras at the far end, when they look at somebody at the other end, they are very, very small. They're only a few pixels. And so it does a reasonable job of tracking these people. Another example on, so this is the cafeteria at EPFL. And what this is showing is what happens when people walk in. So we're not telling the system how many people there are. It just figures this out for itself. So it basically what happens when blobs start appearing, it decided it needs to explain them, and it starts doing so. And what it's showing is, of course, the identity is preserved reasonably well. And one important thing about this is in the sequence, appearance is not used at all. The only input are the binary blobs. And here's another thing where we have people, this is just a basketball practice, just put the cameras, and we get something like this. And finally, here's an example that actually surprised us about. So I don't know if you've heard, but every year there's this PETS competition where various algorithms that do surveillance, there's a competition. And so we participated in 2009. And at some point, I don't know why, they decided to run it on this monocular sequence. Where it still does a reasonable job. So I'm not going to claim it works for all monocular sequences. It works for this one because the cameras are reasonably high, which means the uncertainty, the monocular uncertainty is still not all that spread out. And then the linking step does the right thing by finding trajectories that go through the maxima.
You do need to know where the ground is.
Yes. So we are really in a world where because we need to know where to draw our avatars. It doesn't have to be flat, but it has to be known. And so little graph said that year at least we did better than the others.
The subway, how do you calibrate the subway because they're so far away? This is just rough calibration.
So in this case, we calibrated on we computed homography for the ground floor, and it's a subway, so there was a ceiling, so we computed another homography for the ceiling of the subway. And actually, if you come to Lausanne, there's an Olympic museum, and we have actually this thing that's running in the museum. So it's been running for several months now. Where you have visitors that can walk in. There's kind of a room here behind with 4 cameras observing them. And they walk in here, they do something in the room, they walk out, and they see the trajectory on these screens as they walk out. And this is actually, first time somebody came to ask us whether we could do that, I was actually very scared. I mean, as Rick mentioned yesterday, we go back a long way, and when I started, nothing in vision ever worked. And the notion that anything could possibly ever work was completely alien to me, and I haven't quite overcome this bias. But actually, they did manage to make it work in a public setting. So of course, I mean, to be honest, this is engineered. I mean, they carefully put the cameras, ensure that the background is the way it should be, etc., etc. But still, it's been working on its own for quite a while now.
So that people getting in, and then when you get out, they see their trace.
They see their trace on that screen.
Yes.
So it's basically the idea. I mean, it's not like broadcast, but we're going to get to that. If you, in a broadcast style application, if you track players, so there is a bit of a delay. So which is what's happening here, right? Because they walk out, it's when they walk out that they see what they've done. But if you are going to show something after the publicity break, of which there seem to be many on TV around here, it's okay. The small delay doesn't matter. Okay, so last thing is I've told you that we don't use appearance. And it's true, up to now, appearance has not been used at all. But in some cases, you do want to use appearance. And sports is a good example where players have uniforms. There are numbers on the uniforms. You want to use this. But the trick is, and I think that's something that's a little bit underestimated in many of the other state-of-the-art approaches, is you don't get this information all the time. So typically for the numbers on a player's shirt, in practice, really, you can only read them once in a while. In most of the frames, it's too blurry, you don't see them right. So you really need something where you see it once, okay, you remember that, you use it, but you do not depend on the fact that you will see it again immediately. And so what we've done is expanded the framework I've just shown you to do this. And the way we do this is the result I just showed you is done in this context where the identities are ignored. Now, to take identities into account, what we do is we take this graph and we expand it where we have one grid per person. So typically in a team, we will have, we know, in that case, we know how many players there are. And so we'll have one grid per player, knowing that we're going to track what this particular person does. And since it's late, I'm not going to go into the details, but what happens is this formalism can be expanded to take into account the identities. So not only the probability of presence, but then it's the probability that player X is there. And it's pretty much the same, it's just a bit more complicated, but it's still a linear program. It's a linear program in which you add one thing that wasn't there before, which is the probability that this particular blob corresponds to a particular person based on its appearance. And if you don't have any information, you just put the same probability on all possible identities. In this way, if you don't know, which is often the case, you can still keep on going. You just say, I don't know, and you don't exploit it. And so it's a very simple extension. It has one drawback, is we are now working on a graph that's much bigger than the previous one. And it starts becoming slow. I mean, we are losing the real-time performance. So the trick that we've used is to first run the algorithm, the appearance-free algorithm, to get the first result where identities are not necessarily preserved or accounted for, and get rid of all the grid cells in which there was nobody, because they're irrelevant, and then rerun the linear programming algorithm only on this subset of the grid cells, so that it's fast again. And what we get is something like this, where we're trying soccer players, or in this case, basketball players. And so this is actually, these are videos from a real world championship somewhere in, I think, the Czech Republic recently. And we are working on this with the International Basketball Federation. And the goal, I mean, this is in collaboration with an actual company, and the goal is, of course, to be present for real at major sports events, basketball first and others, if we can, in the not-too-distant future.
What are the numbers here?
This is just a frame number, I think.
Oh, the red and green.
Okay, so, yeah.
The team number.
So here what we are, in this video, we are only taking, the appearance we are taking into account is just to what team you belong.
Okay, so it's not trying to track player identities.
No, it's groups. So we have the green team, the red team, and the refs. And in a different version is we could, of course, also look at the numbers on the backs of the shirts, which we're not doing on this video. Okay, so to conclude, what I've presented is an approach that is robust and can track arbitrary numbers of people over long periods of time. I mean, like on the scale of a basketball game. We do not require appearance information. We can do quite a bit without it, but of course, if you have it, then you can use it, and we get real-time performance. So this is not the end of the story. I mean, there's still a lot to be done, which is one of the weakest part of all this is to rely on background subtraction, because we all know that it doesn't work. There are many cases in which it doesn't work. So one idea would be to replace this by a people detector. If you want to go to much more crowded scene than those, it's going to be required, or to a Kinect if you want. I mean, use more sophisticated templates to model other things. I mean, people actually in that kind is pretty nice, because if you modeling them as just a cylinder is pretty much good enough for many things. But if you want to detect also cars, you want to go in the street and detect people and cars, which may move, then you are going to need more sophisticated templates. But the formalism ought to support this. It's just different kind of rectangles. And finally, right now, there is no behavioral model whatsoever. I mean, the only constraint is you cannot go more than a number of grid cells between time step. That's it. But of course, we know there is more to it than that. And for example, in the basketball case, we should also track the ball. And obviously, what the players do and where the ball is are not independent. And so this should be taken into account. So these are the kind of things we're going to keep on working on. And of course, if you're interested, so there are the papers, and more maybe just as important is the software is actually available on the web, and we are of course always delighted when people use it. Okay. Thank you.
Does K-shot path algorithm require the paths to be disjoint?
Yes, the paths are disjoint, but they are because people are never. I mean, one of the basic assumptions is no two people can be in the same location at the same time.
Maybe if they have each other.
I'm sorry?
If they have each other.
That won't work. Okay, so we are not.
Basketball maybe.
But even if they hug each other, they will be at two different locations. If they are on each other's shoulder, then the assumption is violated. But if they hug together, unless, I mean, the grid cells are small enough that they have to occupy two grid cells. So the one thing that will create problems when you don't have appearance, and that's a standard problem, and is this is hard, right? Because whether there are cases where you can see that. So is this they came and they, or is it that? And that's without appearance. There's no answer. It's going to do something arbitrary. The one thing that the appearance thing does well is if it's read the number here, so number 1, once, and it reads it again here once, then it will do the right connection.
So you mentioned that you always do 100 frames. Do you find that if you do 100 frames, it's like the frames in the middle do better than the frames at the two ends?
I thought about it. No, it's about.
I think
there's no obvious. Well, you would imagine the ones in the middle would be the better, right? But we haven't not looked at it systematically.
Okay.
So.
But your experiments, you just chop out the video.
Yeah.
100. Right.
No, basically, we take overlapping things and then we.
Oh, you do the overlapping. Okay.
Okay.
Thanks.
Thank you.
Thank you.